All right. So let's go ahead and use what's called a combinatorial argument, which basically uses like a bijection to show that things are equal. Okay, so in this problem right here, we want to show that n choose r is equal to n choose n minus r. Now, I mean, we don't really have to use a combinatorial argument. We could just use some algebra. So n choose r is equal to n factorial over n minus r factorial times r factorial. And n choose n minus r is equal to n factorial over n minus r factorial n minus r factorial. So you see like n minus r factorial, those match. And n minus r, that's just r factorial. Okay, so yeah, we can use algebra, obviously, to solve this. But we can also use what's called a combinatorial argument. So let's just imagine this, right? So what does n choose r really mean? That means that from n different people, or n different distinguishable items, I'm choosing r of them, right? So, okay, so let's say I am forming an r person committee. I basically have n people to choose them from. Okay, that's great, right? And so what does this mean? This means from n people, I choose n minus r of them. Okay, so how are they the same? So here's like an idea, right? Instead of using n and r, I'll use like a number. Let's say I am choosing 3 people to be a part of a committee from 10 people. So I can do this in like 2 different ways, right? Like I could just choose those 3 people directly and I would get 10 choose 3. Or I can choose not the people on the committee, but I can just choose the 7 people who I just do not want on the committee. And that would imply the people who are on the committee, right? So instead of just choosing the people who are not there, just choose the people. Instead of choosing the people who are there, just choose the people who are not there. So for that reason, 10 choose 3 is equal to 10 choose 7. And in general, n choose r is equal to n choose n minus r, like as you can see right there. Okay, so now here's another question. Prove the sum of the binomial coefficients for a given n is equal to 2 to the power of n. So basically show that the sum from k is equal to 0 to n of n choose k is equal to 2 to the n. Let's go ahead and kind of write this out, the sum. So it's like n choose 0 plus n choose 1 all the way until n choose n, and apparently this is equal to 2 to the power of n. Okay, so here is how we can kind of think about this, right? So if I can show that this is like 2 different ways to basically solve the same problem, then effectively that means they're equal. There is like a bijection, which is like happening internally. Like again, like even in the above example, we didn't like formally show that there is a bijection, but there is a bijection. But yeah, if we can figure out like, okay, if this is 2 ways to count the same thing, then we know they're equal. Like, and really who wants to actually go through and expand all this, or like it's not the nicest of things, right? So what is 2 to the power of n? Well, 2 to the power of n, we can kind of imagine this. Well, 2 to the power of n is the number of subsets of, like, if I have a set of size n, 2 to the power of n is the number of subsets. So if I have a set A, let's just say that the size of the A is, the cardinality of A is n, then the number of subsets, if I wanted to write it like this, then the cardinality of the power set of A is equal to 2 to the power of n. They're 2 to the power of n subsets. Okay, and why are there 2 to the power of n subsets? 2 to the power of n subsets because for each element, I have two choices. Those choices are include it, don't include it. So I have two choices. So if I imagine like I have 1, 2, I have like n of these, right? And for each of these, I have two choices. The total number of ways, like total number of choices I have is 2 to the power of n. Okay, so now in the power set, right? Like in the power set, I can choose subsets without anything, right? Like that's just the empty set. I can choose subsets with exactly one element. I can choose subsets with exactly two elements, and I can choose subsets with exactly n elements. So in general, like n choose k is the number of ways I can choose k elements from my set, the number of ways I can choose a subset of size k. Okay, so since n choose k is equal to number of ways to choose subsets of size or cardinality k, then n choose 0 all the way until n choose n is the number of ways I can choose subsets of any size. And I'm obviously adding them all up, but I'm not going to write like every single one of them. Okay, so that means based on this, since I'm solving the same problem in two different ways, that means that this sum right here does have to equal to 2 to the power of n. All right, let's go on to the next question. Okay, this one is quite a good question. I do remember the first time I saw it, I had no idea how to do it. So if you don't know how to do it, that's totally fine. But here's a question. How many non-negative integer solutions are there to x1 plus x2, so on until x6 is equal to 20? Okay, so for example, here's like a solution, right? So I can have x1, x2, x3, x4, x5, x6. A solution is like 1, 2, 3, 4, 5, 5. But I have to find out how many different solutions there are. And notice for one thing, these do have to be non-negative. So the idea is, okay, let's figure out a different problem. Let's kind of make a bijection. So this uses a technique called stars and bars. I'm going to use it for a smaller number just because there's like a lot. These are kind of big numbers, right? Let's say it's like a different problem. Let's say it's just like x1 plus x2 plus x3. And let's just say that's equal to 6, right? Like again, this is Like, of course, this is small enough to where we can list them out. It would be time consuming, but I guess it's small enough, but let's try to understand the technique with this. So the idea is the following. So six is made out of 6 ones, right? So you can imagine that the ones are these balls. 1, 2, 3, 4, 5, 6. And then I have these 2 lines here. You'll see why I have 2 lines. But let me like consider different arrangements of these like balls and then these lines, right? So let's say I have this arrangement right here. So what this corresponds to is a specific solution. This corresponds to x1, x2, x3. There's only one ball here, so 1. There's only one ball here, so 1. And there are 4 balls here, so 4. So this corresponds to a particular solution for x1, x2, and x3. Okay, if I have this arrangement up here, right? There's 0 balls here, there's 0 balls here, and then there are 6 balls here. So this corresponds to this solution. But pretty much the idea is that, okay, every reordering of these balls, and then these sticks, or these stars and these bars, that's what it's popularly called, corresponds to a different solution to our answer. Okay, and this is also unique too, right? So you can see that it's both like surjective and it's injective. Okay, every reordering maps to a solution. If I have the same reordering, it maps to exactly one solution. So it's like surjective, injective, so it's a bijection. But in any case, my answer is just the number of reorderings based on that, right? So how many reorderings are there for, like, if I have 6 of one thing and then I have 2 of another thing? So the number of reorderings is just 8 factorial over 2 factorial, 6 factorial. And maybe you can take some time to see why that's the case, but this is the number of reorderings. And it turns out that this is actually just equal to 8 choose 2. Okay, so for our problem up here, I'll actually let you solve it, but you can figure out what it is. It's going to be something, choose something. Okay, we just have bigger numbers, but the idea is like the same. All right, next question. Show that the number of ways to form a committee of size k from n people, where one specific person has to be in the committee, is n minus 1, choose k minus 1. Okay, this one I'm not going to like be super formal, but here's the idea of how we use a combinatorial argument. Okay, so I already have one person in the committee, so they're guaranteed to be in the committee. So I'll just say guaranteed, one person is in committee. Okay, now at this point, I have to choose the other people in the committee, right? And how many people do I have to choose from? Those are 2 things to think about. Okay, now I need to choose the other k minus 1 people from the remaining n minus 1 people, from like my remaining choices of n minus 1 people. And what is this? This is just equal to n minus 1, choose k minus 1. So we can see, right, like the number of ways to form a committee of size k is n minus 1, choose k minus 1. All right, so next problem. Show that n choose k is equal to n minus 1, choose k minus 1, plus n minus 1, choose k. So this one's a little bit trickier, but we'll go ahead and do it, okay? So first thing to realize, right, it's like this n minus 1, choose k minus 1. It's kind of similar to this problem from above, right? And that's a really important problem solving technique, right? Like a lot of smart people, they're not smart because they're smart. They're smart because they kind of have this database of similar problems in their minds, like similar problems which they've solved. So they're able to see these patterns and these similarities. And like that's why they're good at what they do. So again, this is the number of ways to form a committee of size k of n people where one specific person needs to be in the committee. Okay, so the natural idea is, okay, if this one guy, he needs to be in the committee, then the other case is he doesn't, he's like not in the committee for sure. Okay, so that's pretty much what's going on, right? So from n, I'm choosing k people. In one of these cases, he needs to be in committee. This one specific person needs to be in committee. And in this other case, like they're like banned from the committee in particular, right? Like I don't choose this one person. I choose anybody but them, right? So I choose one of these n minus 1 other people. So in this case, this guy, he is banned from the committee. But these are both like at the end of the day, we're still like picking k people. And this one, it looks like we're picking k minus 1, but we've like pre-selected like this person. So these are just like two different ways to choose k people. And it's basing on like the status of whether or not this one person's in the committee. But at the end of the day, that's still equal to n choose k. So that's a combinatorial argument for why this is true. All right, this one. Prove that the number of ways to arrange n people in a line such that no two specific people are not next to each other is n factorial minus n minus 1 factorial times 2. Okay, this one, I think this is kind of a standard counting question, maybe not so much reliant on a combinatorial argument, but that's okay. This is an example of complementary counting, actually. Okay. So I'm not going to write the solution for this, but I'll just give you two hints. Uh, so this is an example of complementary counting. And if you don't know what this is, you can look at one of my previous videos where I talk about it, or you can just look it up on the internet or wherever. You'll see a lot of examples. So it uses complementary counting, and it also uses this other technique, right? Like if I have two people, and if these two people are next to each other, then I kind of like treat two people as like I treat those people as one person. And again, it's really sounds kind of strange, but I'm treating two people as one person for the sake of counting. And if that's vague, that's okay. I'll let you figure it out. And that does deal with this case, by the way. Like I'll just say that these are related. Okay, let's do another very classical example of using a bijection. So let's say that I have this rectangular grid and I'm trying to count the number of ways I can start from the bottom left to the top right corner. And I'm only allowed to move up or to the right. So for example, here's one path. So pretty much I go up 3 times, up, up, and then I go right 5 times. So that's a path. Another path is maybe like this. So right, up, and then a few more rights. Uh, yeah, I think. Oh yeah, and then I have to go up again. Okay, so yeah, that's what I was missing. So I have an up. Okay, so yeah, these are 2 different paths, right? So the question is, how many different paths are there from the start to the end? Well, there is a way in which we can solve this, and the idea is that there's a bijection between each path and each reordering of these letters. So basically, every reordering of these letters, these 3 U's and 5 R's, it corresponds to a unique path. And every unique path, it corresponds to one of these reorderings. So as we can see, like it's injective and it's surjective. So it's a bijection, right? And that does give us the answer. So the question is, how many reorderings of 3 U's and 5 R's? Well, I won't tell you the reason, but I'll just tell you the answer. You should be able to do this at this point. It's 8 factorial over 3 factorial, 5 factorial. And alternatively, that's actually equal to 8 choose 3. Okay, and here, actually, I'll just tell it, right? Like, of course, you can do 8 factorial. You can divide, to account for repeats and whatnot. But here's like another way to think about it. It's like I have 8 different positions, 1, 2, 3, 4, 5, 6, 5, 6, 7, 8. And of these positions, I have to choose 3 of them to be ups. So maybe I can choose this one and this one and this one. So these are going to be ups, right? And the rest of them, they're going to have to be R's. Okay, so it's like from these 8, I'm basically just choosing 3. Okay, so you can see like the number of reorderings is a choose 3. All right, so that is going to be the end of this video, and I will see you in the next one. Thank you so much.